Hi, good afternoon. Now let's move into the network issue and now let's begin. Interesting vibration dynamics and the material behavior and travel also too. Biomechanics, interesting topic. Okay. If you have a strong background in the solid mechanics, FEA and tribology, so you should like that. My work focused on the on-site wear analysis of a heavy-duty piston cylinders unit, where I used analysis and optics to correlate stress and thermal fields with the real wear patterns, often through the ferrography. Uh, and there is the my research direction, especially to the computational mechanics, contact mechanics, and tribology driven design. And I would like to work different fields like solid mechanics, computational modeling, and machine design. Oh, focused on-site wear analysis, heavy-duty piston cylinder and unit and coupling, experimental evidences with the numerical solutions. Experimentally, I collected wear debris using the ferrography, measured surface topography before after the test, and monitored operating temperature and lubrication conditions. Numerically, I built the thermomechanical contact models analysis to predict the contact pressures, temperature distribution, and stress fields in the piston ring cylinder interface. I used OptiSlang to run sensitivity and design space explorations, identifying which parameters and clearance, surface roughness, oil viscosity, operating speed temperatures most strongly influence predicted wear rate by correlating predicted high contact pressures, temperature zones with actual ferrographic debris and surface wear patterns. I validated the simulations and produced a small set of the optimized design and operational recommendation to reduce the wear. The work integrates tribology, FEA, and optimization, points to physics informed predictive wear modeling for engine components. You know what? Deriving, I enjoy deriving the models for the first principles, stress, contact dynamics, and then using the computational tools in tribology and FEA fits naturally. The department offers the strong expertise in contact mechanics, computational methods, and experimental validations, which is exactly where I want to contribute. Existing wear models for the piston cylinder system often treat contact thermal lubrication effects separately or use the empirical correlation that lack the predictive power across the operating regimes. The research gap is mechanism aware predictive models that couple thermomechanical contact, surface roughness, and transient lubrications, and that are calibrated, validated by the experiments, ferrography, surface, metrology to predict the wear across duty cycles. My work begins to close that gap but needs more for multiphysics coupling and data driven model refinement. Validation steps I followed while using the ANSYS software. To mesh convergence study, refine the mesh in the contact zones until the key outputs peak contact pressure, maximum temperature converge. Benchmarking, compare simple cases with the analytical solution, Hertz contact, 1 degree of the freedom, vibrations where applicable. Experimental correlation map predicted high wear, high temperature regions to actual wear scars and ferrographic debris and compositions distribution. Parametric sensitivity check that trends with the changing clearance, speed, or viscosity match. Experimental trends error quantifications report percent differences for the measurable quantities, example contact temperature plus minus X% wear depth trends. OptisLang, interesting software. Okay, OptisLang provides automated sensitivity analysis, robust design optimization, and reliability analysis. I used it to identify dominant parameters affecting wear global sensitivity, run design of experiment and surrogate models to explore the parameter space efficiently. Find the robust parameters, sets that minimize predicted wear under the variability, material, temperature, clearance. It saved computational time by guiding which combinations to simulate at the high fidelity. What simulation parameters affect wear predictions the most? Most influential parameters, contact pressure, loads directly affects aesthetic, contact and adhesive or wear. Sliding speeds or relative velocity affects the frictional hitting and regime. Temperature, viscosity, reductions and material softening. Lubricant, viscosity and stray-back parameters. Boundary versus mixed versus hydrodynamic. Surface roughness and topography. Asperity contact area, material hardness or mechanical property, yield strength and hardness. Contact model choices, friction's law, adhesive versus Coulomb adhesion coefficient, mesh resolution in contact region, affect the stress, pressure, prediction accuracy. Now, boundary lubrication. It is an important concept. Okay, to film thickness is comparable to the asperity heights. Asperity's contact friction and wear governed by the surface chemistry, absorbed films and the surface roughness. Mixed lubrications, partial separations. Hydrodynamic film supports some loads while asperities still contact in the places frictions and wears are the lower than the boundary but higher than the fully hydrodynamic. Strip back curve shows transition from the boundary. Mixed hydrodynamic as the product of the viscosity into the speed upon the load increases. How does cylinder bore deformations affects the wear? First of all, no, they're mainly basically depend on the four parameters: no geometry change, misalignment, thermal expansions, and the dynamic deformations. So let's explain a little bit. Geometry change alters the contact pressure distributions, ovalizations, or tapering causes localized high pressures, increase the local wear, misalignment, increases the edge loading on the rings, edge wear, scuffing, thermal expansion changes the clearances and reduce the clearance. Reduce clearance raises contact pressure and friction. Dynamic deformation, whirling vibration can cause transient asperities impact and accelerate the wear, controlling the stiffness and thermal management and manufacturing the tolerances and mitigate these effects. The more circle for the given stresses and how to do it. Okay, explain simple procedure. Contact stiffness quantifies how contact force changes with the relative approach penetration of the two bodies. Essentially, Kc equal to the. Now let's let it. Over constraint statically indeterminate system has the more constraints than the necessary leads to the internal stresses from assembly tolerance variations and thermal expansion problems unknown reaction distribution binding unpredictable load paths difficult assembly solution introduce compliance flexors, kinematic constraints, exact number of the constraints, use compliant mounts or the data system, tolerance allocation or redesign to a kinematic couplings. Nonlinear geometry. Nonlinear geometric behavior arises when the deformations are large enough that initial and deformed configuration differ significantly, affecting the equilibrium equation. Example, large rotations, large strains, buckling, contact with the large relative motion. In FEM, geometric nonlinearity requires updating stiffness, tangent stiffness, and using incremental iterative solutions, Newton-Raphson's. No, future research goals for the short term, I decided to develop a validated multi-physics predictive via model for the piston-cylinder interfaces, combining the contact thermal coupling, surface roughness, modeling, and lubricant behavior. Long terms, I decided to create a hybrid physics and data driven frameworks for the predictive maintenance and design guidelines that generalize across the engine types and operating regimes. Some strengths requires like that computational mechanics skills FUN analysis and practical tribology and experimental experience, photography, surface metrology, experience with the design, optimization, OptiSlang, ability to connect experiments and simulations and communicate results clearly. Okay. And biggest challenge in the VR modeling capturing multi-scale, multi-physics coupling reliably, how microscale asperity interaction surface chemistry, lubricant film behavior, and macroscale contact and temperature interact over the transient duty cycles. This requires good experiment for calibrations and robust computational approaches. Ferrography lubricant sample analysis, where the wear particles are separated magnetically and examined microscopically. It provides particle size distributions, morphology, and composition, ferrous versus non-ferrous, which helps identify wear mechanism, adhesive, abrasive, fatigue. I use it to correlate the particle characteristics with the operational conditions and simulation predicted wear zones. And my thesis focused on the site via analysis of the power cylinder piston unit in heavy duty diesel engines using ANSYS simulation coupled with a ferrography based experimental validation. I built a numerical via prediction framework, optimized the parameters using the OptiSlang and correlated via particle morphology with the predicted stress strain fields to provide a predictive maintenance models. Most VS studies treat engines as the static or simplified contact system. Real engines experience coupled thermomechanical deformations, dynamic lubrication changes, and the multi-scale Weir particle evolution. Capturing this coupled phenomena is the primary research gap. I validated result using the ferrography, comparing particle size, shape, severity index with the stress concentration, predicted wear distribution from the analysis, the correlation between the high stress zones, abrasive wear particle patterns, confirm the model accuracy. OptisLang was used for design optimization, sensitivity analysis, and building a meta model to identify which parameter influence were the most were most. It reduced simulation cost and helped find the optimal combination of the pressure, temperature, and material properties. What simulation parameters affect the wear prediction the most? Contact pressure, sliding velocity, lubricant viscosity, temperature dependent material properties, surface roughness. These parameters directly affect the contact stress and lubrication regime, where hence wear rate. Boundary lubrications. Surfaces are mostly in contact. Lubrication film is insufficient and wear is dominated by the adhesion abrasion. Mixed lubrication, partial film exists. Load is shared by the fluid film plus asparity contact and wear reduces significantly compared to the boundary regime. How does the cylinder bore deformations affects the wheel? Deformation changes the contact pressure distribution, causing the non-uniform oil film thickness. Local thinning leads to the boundary lubrication spots, which accelerates scuffing, microabrasion, and ring wear. What experiment method do you use? I used analytical ferrography to study the wear particle. It provides particle shape, morphology, severity of the wear, distinctions between adhesive, abrasive, corrosive wear. This helped validate simulation results. Large deformations, finite strain, geometric nonlinearity, post buckling, elasticity, linear, nonlinear elasticity theory, stress strain relation, composite material and structure, laminates, fiber reinforced materials, anisotropy, delamination analysis, plates and cells, classical and higher order theories, bending, vibration, buckling, structural stability, buckling of the column, cells, plates, nonlinear stability analysis, dynamic plasticity, rate dependent plastic deformation under the dynamic loading, shock or impact, damage mechanics, continuum damage models, crack initiation, progressive failure. Functionally, graded material structure, material property variations across the structure, stress, and thermal analysis. Now, research proposals and the pitch. Title: Multiphysics Modeling and data-driven prediction of the wear and structural response in the engine and bio-inspired system. The research aims to develop a predictive models integrating FEA, tribology, and AI for the mechanical and bio-inspired system using ANSYS and OptisLink. The project will simulate contact mechanics, large deformations, and material heterogeneity. Experimental validation by the fairography, surface characterization will ensure predictive accuracy. Applications include engine components, smart structures, soft robotics, and biomedical devices. Objective developed multiphysics FEA models incorporating contact thermal material nonlinearities, perform wear and damage analysis for the piston cylinder and composite structures, apply AI ML tools for predictive modeling and optimization, explore biomechanics applications. Example, soft tissues, wearable devices, and cardiovascular modeling. Large deformations and nonlinear dynamics. Piston cylinder FEA under the high load and thermal stress and low rotor engine dynamics. Composite material, plastics or the cells. Tribology and wear modeling in the layered materials or coated surface. Structural stability or dynamic plasticity. Predicting the failure due to the misalignment, high load, or impact in the engine components. Nanocomposites multi-scale modeling. We are at the micro and nano scale predicting particle-induced surface damage. Biomechanics, soft material, and soft robotics. Apply the contact mechanics, FEA, and the tribology concepts to biomedical implants or devices. Piezo, piezo thermoelasticity, smart structures, future applications in the smart sensors for structural health monitoring. AI digital twin wearable robotics using the simulation plus AI to predict the component's life and real time monitoring for the engine or the biomedical devices. How did you correlate simulation with experimental ferrography? I compared predicted high stress region from ANSYS with the weird debris morphology and distribution from the ferrography. For example, Jones with the high contact pressures in the simulation aligned with the regions showing abrasive or the fatigue wear particle. I also checked the trends and how changes in the loads, temperatures, or lubrication affected wear in both the simulations and experiments to validate the model. Which parameters most affects wear in the piston cylinder assembly? The most influential parameters are contact pressures, load, sliding velocity, engine speed, lubricant viscosity, and the type, temperature affecting material softening, lubrication, surface roughness, and texture, material hardness. This directly control the lubrication regime, friction, and resulting wear. How would you apply your experience to the soft robotics or biomechanics? Same contact mechanics, via modelings, and multi-scale FEA approach can be applied to the soft robotics or tissue mechanics. For instance, soft actuators experience the large deformation, friction at the interface, and the fatigue is compliant materials similar to the piston cylinder contact. My expertise in simulations plus experimental validation plus optimization is transferable to designing durable, efficient, and safe soft robotics or biomedical devices. Multi-scale modelings. Role of the multi-scale modelings in predicting the wear or tissue mechanics. Multi-scale modeling links micro nano level phenomena, asperity, contact, and microstructure cellular deformation to the macro level behavior. Overall wear tissue stress, it allows accurate predictions of the failure deformations, or the wear evolutions by the incorporating the material heterogeneity, surface interactions, and the microstructural effects, which is the critical in both the engine components and biomechanics application. How can AI and the ML enhance your research in mechanics or smart structures? AI and ML can create the predictive surrogate model for the complex FEA simulations, identify hidden correlations between the operational parameters and the wear or the failure, enable the real-time monitoring and predictive maintenance in the engines or the structural health monitoring in the smart materials, optimize the design parameters faster than the full-scale simulations. Contact stiffness quantifies how resistant a contact interface is to penetration in FEA. It determines convergence behavior of the contact simulation, accuracy of the predicted stress and pressure distribution, correct representations of the contact load transfer, which is critical for the wear frictions and deformation predictions. How do you account for large deformations or nonlinear material behavior? I include geometric nonlinearity, large displacement or rotations, and material nonlinearity, plasticity, hyperelasticity in FEA. This requires updating the stiffness matrices incrementally using the iterative solvers Newton, Raphson for the wear studies or the soft robotics. This ensures the simulations captures true stress and strain contact behavior under the realistic operating conditions. How does tribology impact the design of advanced composite or smart material? Tribology informs the material selections and the surface design and lubrication strategies in composites or smart materials. Surface wear affects the performance and longevity. Frictions affects actuation's efficiency in the smart structures. Proper tribological design ensures reliability under the dynamic loading, whether in the engine components, soft robotics, or biomedical devices. No thanks. It is a nice delay. Let's meet later for the with more interesting talks. Okay. Thank you.